Here we go. We're going to go in this order: perfectly inelastic, inelastic, and then elastic collisions. So that'll be the order: perfectly inelastic, inelastic, and then elastic collisions. So we're going to start with a perfectly inelastic collision. And let me preface this with the statement that in a perfectly inelastic collision, the two objects are going to couple together due to the collision, which will mean that they are going to have a single velocity. They are joined together. They have a coupling. So imagine one train car being run into another and them having a combined velocity after the collision. We'll go with 4 meters per second that way and 2 meters per second this way. I think the obvious question is, how fast are they going after the collision? Now, I don't have to say that they join together if in the course of the problem I state that it's perfectly inelastic. So be aware of that. That's a vocabulary word. They don't have to tell you that they join together. They also don't have to say it's perfectly inelastic. They can say that they couple together, but it means the same thing. The first thing I want you to be very cognizant of is momentum is a vector. So you are encouraged before you get started to try and decide what direction you will call positive for your momentums and your velocity. And if you've been in my room before, you know that I set up every collision the same way. I draw it all out with a before side and an after side, and I kind of believe the collision is where the line is, and I always draw an arrow on top of that line to indicate the direction that I call positive, so that I am remembering to deal with vector information. I make all velocities that are unknown positive. And if through the course of the work the value comes out to be negative, then I know. But if my velocity is unknown, don't explicitly put some negative sign in front of it. Just put a placeholder there, V, and solve the problem. If it's going to be negative, it'll work out in the problem that it's negative. We're going to start, though, with recognition that the momentum before the collision has to equal the momentum after the collision. I like to make sure that we remember that there are two items, both before and 2 items after. It is clearly plausible that you could recognize these 2 objects as one. There's nothing wrong with that. Mathematically, it's fine. In fact, that's what I typically do if I know it's perfectly inelastic. I will caution you, though, that when you're dealing with momentum, you really do need to be very aware of the direction that you call positive and be working from a standpoint of recognition of negative velocities. Expect them. Now, from this point forward, the problem is pretty mundane. It's a mathematical exercise. So I've got 4,000 minus 1,000, or 3,000 kilograms meters per second. This represents the momentum of the system. Don't be thrown off if you're asked for the momentum of the system at some point in the problem. Be able to report it. This is the momentum of the system. And they might ask you, what is the momentum of the system after the collision? It's still this. The momentum has to be conserved, so the momentum before the collision is equal to the momentum after the collision. That is what we are saying here. That has nothing to do with figuring out the velocity after the collision. That's just a statement of how to deal with the problem. But solving for the velocity isn't all that tough. Now, I will state something for you guys that I haven't yet, and that is, I didn't put the units for the mass of the cars. And this bothered somebody in third period. Look, these could be, model trains. They wouldn't be 1,000 kilograms. I doubt they'd even be 1,000 grams. But 1,000 grams makes a lot more sense for a model than it does for an actual size train. You don't have to change the mass from grams to kilograms if what you're searching for is velocity. As long as everything is in the same unit, the mass part of this would cancel out. Now I put the kilograms here because I'm saying these are big trains, sure. But just be aware that if you're not looking for the momentum or the impulse or the momentum of the system, you can leave your units the way you'd like. Make them easy to work with if you'd like. But I think all of us know velocity is 2 meters per second in this case. This is not what you're going to have to do on the exam. This is a minor part, part F or part D for a multi-part question. They're not going to make the entire problem about this one perfectly inelastic collision. There are a couple of all momentum FRQs out there, but they are few and far between. Now, I'm not trying to dig one of those out for your exam. However, if there is a all momentum FRQ, it's mostly going to be laboratory data kind of FRQ, meaning a collision probably with a graph of force and time where you're going to be finding the area under that graph. And if we have enough time, we'll make it to one of those here in a bit. It could be a part of a problem like this. I want you to imagine if this was part A of the problem, what do you think part B and C of the problem look like? Part B could be a discussion of impulse. And I'm not sure this is particularly clear out there, but each car during that collision experienced an impulse. But it should be clear to you that the impulse of the system is 0. Now, I want to be very clear because I don't think that people put the pieces together. Look, I did a multiple choice retake this morning. A lot of people made new mistakes on this one. But it wasn't because they're not intelligent. It's because they're making mistakes with the details. The details are what dog you guys quite a bit. And I'm expecting you guys to come to conclusions, and you can't always. Impulse is change in momentum. In a collision, the momentum stays constant, suggesting the system experiences no change. So by definition then, the impulse of any collision should be 0 for the system. But the individual cars are going to experience impulses. We know that car number 1 had a clear change in momentum. Although its mass didn't change, it went from going 4 meters per second to 2 meters per second. A change in momentum of negative 2,000 kilograms meters per second. Now, it should be obvious that the other car experienced a 2,000 kilogram meter per second impulse. That's positive. If the net change in momentum is 0, if one car experienced a negative impulse, the other one had to experience an equal and opposite positive impulse. So, I don't think it over the top for us to look at the change in momentum of the other car, which went from negative 2 to positive 2. Right, the velocity, which will give me my positive 2,000 kilograms meters per second. Net momentum change, 0. Now, this might be a little bit of a surprise to you guys, but I really hope it doesn't, that in any collision, the derivative of any equation for momentum has to be 0 for the system. That also must be true. So if you're given some kind of equation, some function of t, the impulse would be the derivative of this with respect to t. That would give you the force. But the impulse would have to be 0 for the system. The net force on the system has to be 0. Now, there was forces here. I could guess that a question C would be to talk about the length of time the two objects were in contact. and then ask for the net force. That really isn't asking very much, but I could see that as a follow-up question. Or maybe they tell you what the minimum force is that these guys can stand before braking, or maximum force before braking, and ask how long they must be in contact before they brake. Yeah, I don't know. Any number of these questions could be asked, all related back to force times time. But I think they're really going to spend more of their, construction of a problem talking about energy. The energy in a collision. Because here's where prepositional phrases tend to get in your way. The kinetic energy of the system is not conserved. Energy is conserved. Sure, that has to be true. Energy is always conserved. That doesn't mean you can track it, but the kinetic energy of the system is not conserved. I mean, I don't want to do the math on it, but 1/2 1,000 times 4 squared plus 1/2 times 500 times -2 squared represents the energy of the system before the collision. After the collision, 1/2 times 1,500 times 2 squared. This represents all of the kinetic energy of the system before there was a collision. So that is the energy of the system. Our system stayed at the same height the whole time. There was no springs involved. So I'm not worried about any kind of potential energies here. On the other hand, after the collision, there's still kinetic energy in the system. The system is still moving. I am confident there's a lot less energy after the collision. Now, where'd that energy go? I don't know. Don't really care. Probably made noise, maybe dented the objects, went into heat. Who knows? That's neither here nor there. What is important for you to understand is they can ask these kinds of questions all sorts of ways. What is the ratio of the final energy to the initial energy? What is the percentage of energy lost? How much energy was lost? What is the change in energy? I mean, they can ask a lot, and each one of these is a subtly different question. If they're asking for the energy lost, will you know to take the final energy and subtract it from the initial energy? I think you should be able to, but we've proved time and time again that you get asked these questions where I think it's not a big deal, but you think they're a big deal. So be careful of the way those questions are going to be asked. They ask for the ratio, then you know you're making a dividing line and you're putting something on top and something on the bottom. That is a ratio. A ratio is going to be a fraction. It can be an improper fraction, but it's a fraction. They ask for how much energy is missing. Well, then you're probably looking for delta. That is the definition of delta, the change. By how much is it reduced? That would be final minus initial. They're asking for the percent lost. Well, then you're probably going to divide this by the K initial. That's how much there was. This is how much is lost. This is a percentage of energy lost. Look, I'm expecting that I don't have to spell this out. But I've been disappointed this year in this kind of stuff. So yeah, I think this is the kind of stuff they'll ask about. They're going to make the problem all about this kind of stuff. Now, the next question I want to talk to you about is one I really won't run through. We'll talk a little bit about it, but I'm not going to do this as an example. And I think you'll understand why pretty quickly. Let's consider the bullet and block question, where a bullet is fired into a block. There are a variety of potential outcomes here. Depending on the composition of the bullet and the block, any number of things can happen. There is the possibility that the bullet will penetrate the block and pass through it. That's a possibility. It is likely while that's happening, it will give momentum to the block. There's, of course, the possibility that the bullet will become lodged somewhere in the block. That's the perfectly inelastic collision we just did. And of course, there is the possibility that the block is impenetrable and the bullet will bounce off of it. And therefore, the block, of course, will recoil away. All of these are possibilities. Now, in creating a collision question, what we're looking at here are the possible inelastic collision options. All of these are possible collision options. Some of them lose more energy than others. There's different impulses in each. What's important to understand from the standpoint of the problem is that, let's say that I am given the initial conditions of the problem. Mass of the projectile times the velocity of the projectile plus mass of the wooden block times the velocity of the wooden block. Who knows what I'm given over there? And afterwards, let's take a look at what we'd have. We'd have the mass of the bullet times its velocity and the mass of the block times its velocity. I mean, no matter what, I'd have to give you enough information so that there's only one unknown here. It's not like I can say, what's the velocity after the collision? If it's an inelastic collision where both objects could be moving, momentum can only generate one relationship. And because it can only generate one relationship, it can only solve for one unknown. So in a straightforward collision, the test writer really has to provide you with a lot of information in order for you to successfully complete the problem. I mean, I'd have to give you one of these velocities in order for you to figure out the other. Now, maybe I'll give you clues, like one velocity is twice as big as the other, or one recoils with half the velocity. I mean, I could do that, but what I'm really doing is providing you with a second equation, something that relates together V1 and V2. But momentum can only produce one equation. That's it. So when it comes to conservation of momentum, you get one shot at it. And if there's more than one unknown, there's got to be some other clue in the problem, something else to help you figure out the other unknowns. That's why most of the questions on the exam tend to be perfectly inelastic. Because just have the bullet get embedded in the block. It makes it easier. On the other hand, we could dive into the realm of elastic collisions. Now, elastic collisions offer us more information. Now, let me be really clear about elastic collisions for a moment. In nature, there really aren't any elastic collisions that you can witness. Elastic collisions occur like at the atomic level. I mean, if you can hear two things collide, it wasn't elastic. Some of the energy was converted into sound. If there's heat generated, if the object was deformed, all of that takes energy. So, true elastic collisions don't really exist in the macroscopic, they exist in the microscopic. That doesn't mean that a lazy test writer can't say that the bullet bounces off the block elastically. If the lazy test writer says that, then they are immediately telling you that both momentum and kinetic energy are conserved. I'm not saying that a dozen times. If the word elastic, or they say that they collide elastically, then they're telling you that the momentum and the kinetic energy are both conserved. That immediately generates another relationship. You now have two equations and potentially two unknowns. And yeah, now they could leave the two velocities unknown and expect you to solve for it. Elastic collision problems are tough. They're a lot of work. They're mathematically difficult because they are a lot of work. They're going to generate two sets of answers. Be aware of that from the beginning. They have to because we have quadratics here, so you're going to get two different sets of answers. It is very likely one of them will be obvious. And let me just spell it out for you. You will always get a quadratic that you have to solve. And in the solution of that quadratic, you will get two answers for V1 and two answers for V2. However, the two answers for V1 and V2 are going to include the initial velocities before the collision. That will always be one of the sets of answers that you get. It has to be. They had two velocities before the collision and two velocities after the collision. So when you solve one of these, you will get back the initial velocities. That's a clue that you're doing it right if you get back the initial velocities when you do this work. It also tells you what one of the roots are when you have to deal with your quadratic. So you don't have to use the quadratic formula if you don't want. It'll factor with one of the roots being one of the initial velocities. I'm not going to do the math here. The likelihood of this being on the exam is so remote, I can't even remember the last time it was on the exam. Meaning I have no vision of the exam where they've asked for a elastic collision solution. Because look at what you have to do here. You're going to solve the top equation for V1 or V2 because it makes the most sense to do it that way. They're not squared. And then you're going to plug that in to the energy equation where you will have to square that equation, which is going to be complicated. It could have 2 or 3 terms in it that you'll have to square. And then you will be collecting a complicated squared equation to which you have to solve it with a quadratic or factoring. They're tough. So they will do things to make them easier, like they'll make one of the object have 0 velocity at the beginning. They'll probably make one mass a multiple of the other. That also makes it a little easier. It generates simpler equations, but you're not getting away from all the math. This question doesn't show up on the exam. So working it out, taking 10, 12 minutes, I mean, at your best, maybe 10 or 12 minutes to do the mathematics here. You don't have 10 to 12 minutes to find one set of answers. What they will ask, and this is what you should be prepared to do, and this is where students fall flat, is they will likely give you one of the velocities after the collision. Ask you to figure out the other velocity. And then ask if it was elastic. Meaning you would have to prove it was an elastic collision. If that's the question you are asked, then you need to be prepared to deal with finding the kinetic energy before and comparing it with the kinetic energy after. Should they be equal? It was an elastic collision. They get to test the same concept with, I don't know, a quarter of the amount of time spent on the math. That you should expect. That'll be on the exam, sure. That could be a multiple choice question. A long one, but still a multiple choice question nonetheless. So elastic collisions, both momentum and kinetic energy are conserved. Now, I want to take a look at an interesting question. At least what I think is an interesting question. And before I launch into it too much today, the one I want to do in this class, the one I want to do in this class is a little bit different. This one has shown up on the exam a couple times, but not for a couple of years. I just like this question because a lot of students don't think about it. And they get so caught up in collisions not conserving energy, they forget that conservation of energy exists all over the place. But conservation of momentum is never violated. I have 2 blocks. I put a spring in between them and I compress the spring. I then release the spring and the 2 blocks split apart. I think most of you in the room would recognize that there is a pretty clear conservation of energy question here. That the energy was in the spring before, And now after, the energy is in the kinetic energy of the two blocks. But alone, that couldn't solve the question. Two unknowns. But this would be the energy portion. On the other hand, momentum can't be violated. The momentum of the system before the spring is released is zero. Neither block is moving. So the momentum of the system after the spring is released also has to be zero. So they don't just get some random amount of energy. The amount of energy they get is actually predicted by momentum. That when these separate, it's not random. And it comes right back down to both blocks experience the same force. Remember, the spring pushes with equal force on both blocks. So the block that is more massive has a less effective acceleration due to its mass. Well, the block that's less massive will be more affected by this force. So the lighter box will be going faster, the heavier box will be going slower, but they will carry away a finite amount of energy. You guys okay with that? Now, this problem we talk about because it's not particularly hard, and it doesn't have to be done this way. There's this version of the problem where the spring is in between them and is then set and released. But there's also this version of the same problem. I'm just going to draw right here. The other version of the problem is perhaps, let's just get all that out of the way. The one block's at rest, the other one's moving. Then they join together and both are moving. And then, I don't know if you know where I'm going with this, but I'm trying to. And then they perhaps separate. And have some independent velocities. Interesting thing about this problem. This is clearly a problem that could be on your test. There are interesting parts to this problem, like what is the maximum compression of this spring? What is the velocity of both carts after the collision? How fast are the carts going when the spring is at maximum compression? These are all interesting questions, and it's hard to know what's conserved and what isn't. But in this problem, momentum is always conserved, and energy is always conserved. And the forms of energy that exist in this problem are ones that we can track, meaning mechanical energy in this question is conserved. Look at what's happening. At the very beginning, if I just look at momentum, the momentum in this problem is pretty easy to track. I've got mv for the first block. This is the initial velocity of that first block. Let's say the second block isn't even moving, so it has no momentum. After the collision, both blocks will reach a point where they have a combined total velocity that is the same. This has got to be at the maximum compression of the spring. Because if the spring wasn't at maximum compression, they would still be traveling at different velocities. Either still compressing the spring or the spring has started to separate. But at the maximum compression, they have the same velocity. So boom, that's how you figure out the velocity of the system at maximum compression. Because it has to be going to have the same velocity. Well, how much was the spring compressed? Well, at that moment, the energy of the system would have to be in both blocks in terms of kinetic and elastic potential. But the system got its energy from the first block moving on its own. Anything new? This is all stuff we've talked about. But you see how you'd be blown away by this. That's why you have such a gifted teacher in the room to tell you things that can happen. You're right. You don't. You just have me. That's why you all are screwed. Which brings us to the final part of the problem where I think you see this is going. This actually, at its heart, is an elastic collision. If we remove the spring from the problem, remove the middle section, after this collision, there's going to be M1V1 plus M2V2. The momentum has to be the same all the way through this problem. But also, there's no place where the energy was converted to another form. So this is a more common elastic collision. And this has been on the exam. Now, if they make these two join together here, it throws all of that out. These two oscillate now. That's not an atypical question. It's been asked, but not that often. This problem has been asked. Not like this. Yeah.
How do you know the velocity at the beginning for the first block is the same as the end?
It isn't.
Oh.
This is VI for initial. Sorry. I am sure that's going slower after all that. This hasn't been asked recently, but just to kind of put it in perspective, the problem is that instead of this being 1/2 kx squared, it's 1/2 mv squared. I'm sorry. It's mgh. Blew that. Here's the way this was asked last. And I'll be honest, I love this question. This one I'm about to show you. It's not a hint. I'm really thinking about giving you this question for the exam. So, or for the test, whatever you want to call it. Because I just like it. See if I can find. I don't have a shape that'll work here, so I have to draw this.
No.
All right, so I know you have to leave, but this is the same thing as the problem you just saw. One block fired at a ramp. Instead of storing the energy in the spring, it's stored as gravitational potential energy as the block climbs up the ramp. Momentum's still conserved, but now when the block is up here, both of these have some velocity. The only difference from the prior... So, folks, I'm not giving you this question because I just put it out of the bag. You can search for this picture. But there's like 5 or 10 different versions of this problem in the literature. It's a great question. It's a good thing to look up. I will have a practice test for you. Let me explain why I'm not going to do this other problem with you guys. This is what I did in AP, in third period APC. I really wish this program had a really simple duplicate function. It would make doing what I'm trying to do right now so much faster. But it doesn't. And that's disappointing. All right. Imagine a bullet is fired at a block. The bullet becomes embedded in the block, and the block and bullet together swing upwards some angle. Let's say I give you this length, I tell you this angle, and I express the mass of these two objects. Let's say in grams. And ask you, based on what you see here, how fast was the bullet going before it struck the block? This is called a ballistic pendulum. It is actually a real device used to measure the velocity of bullets. They are a little more complicated than this, but not much. The nice thing is almost anybody can set one of these up. And if you're into ballistics, this will work. I'll tell you how fast the bullets are going. You have to measure this angle. So generally you have to have something that will tell you what the max angle was, because the object will be swinging after you're done. But luckily for you, if you get out there fast enough, it'll probably still be swinging at the right angle. Usually they use something else to measure this angle, though. Camera equipment or something. What you have to understand is that this problem combines conservation of energy and conservation of momentum, but you have to know when to use each. That's what the AP exam is really about. It's really about not knowing the rules. You have to know the rules. It's about discriminating, about when one rule should work and when a different rule should work. This one is pretty clear. They won't always make them this clear. But momentum is not conserved while the box is swinging upwards, because the box is being brought to rest by the force of gravity. So the velocity is changing. There's an external force on the system that's acting to take away velocity. So momentum is not conserved there. That's not unusual, because in that particular case, the box is swinging to a higher position. It should trigger in you conservation of energy. That's at its lowest point when the bullet enters the block, and it swings upwards, coming to rest. So it has no kinetic energy at its maximum angle. So those will be equal. But there's also a clear collision, a moment where the momentum of one object is imparted to the momentum of another, a force applied through contact. Energy is probably not conserved there, but momentum must be, because of the instantaneous velocity of the bullet before the collision compared to the instantaneous velocity of the bullet in the block after the collision. No external force has enough time to cause any change in momentum, so you have a conservation of momentum problem here. Moreover, this problem is worked backwards. I gave you the angle. You would have to use that to figure out the velocity just after the collision, which you would then work backwards to figure out the velocity before the collision. This problem is fully done during period 3's exercise. You should look at it. But I would do the math here if I were you before you go check it, paying special emphasis to understand that H and L are related somehow. And if you haven't memorized this yet, phooey on you. Right? All right, let's look at our